My name is Matt Whitehead. I'm here with Descartes Labs, and today I'm going to be talking about leveraging FOSS to develop an OSINT visualization and analytics framework. Is anybody here familiar with the term OSINT? There's people. Good. So for those that aren't, that's the process of gathering and analyzing publicly available information to make decisions and assess threats. And in our case, we're looking at people's access to the internet as a possible indicator for something else, something potentially nefarious. So an overview, I'm gonna kind of lay out the problem so we understand what we're looking at. I'm gonna do a system architecture overview, and that truly is an overview. I'm not gonna talk about all the individual components. I'm just gonna pull out, the pertinent FOSS pieces, and then I'll talk about them in a little bit deeper dive. And then I'm going to brave a live demo, but I do have backup images, but internet seems to be working pretty good, so we should be able to look at the application, or at least the front end piece. And then I want to discuss future work. So this is developed as a framework. We are going to be iterating over this for the foreseeable future. There's a lot of stuff that you won't see. It's, infrastructure is code. Nobody wants to see that. It's not exciting. So, but we've built kind of the framework to be able to build off of this. So understanding the problem, from an OSINT analyst perspective, rapid decision making is important, and workflows are often slow and cumbersome. And a lot of that has to do with the data. Quality, complexity, update frequency, the structure, it's all over the board. So what we're trying to do is create a single pane of glass is what we call it, for users to view data products and analytic derivatives using that open source data. And again, I'll just reiterate, it's designed to be extensible. So to sum it up in one sentence, we want to transform complex signals into measurable intelligence through a single pane of glass. And what we're looking at doing is providing this information at a global scale, which brings its own issues in terms of data. But we are collating global OSINT data, creating automated data pipelines, the ability to upload your own data, customizable visualizations. We are not trying to recreate WebGIS. This is more of a situational awareness dashboard, but there are some of those traditional kind of GIS features. We also look at time series, looking at doing analysis and anomaly detection. We're trying to establish patterns of life to be able to alert if something changes. And then a big push for interoperability and integration. Right now it's all in AWS. So moving on to the system architecture overview. Again, this is an overview. And I'm just pulling out the pieces that are relevant here. So we're looking at open source data, all different sources. We've kind of narrowed the scope for this application. As we iterate over it, we plan on adding additional data sets. One of the bigger data providers is a program called UNI, and if you just Google UNI, you're going to get pizza ovens. But UNI stands for the Open Observatory of Network Interference. It's tremendous data, a big community around it. They're very responsive on Slack, which makes it easy for me. So that's one of our bigger data sources. Also things like Open Cell ID, which is an open cell antenna database, and other sources. For workflow orchestration, we want observability into these ETL pipelines. Airflow is a very common workflow orchestration tool for ETL, but we adopted Metaflow, and I'll touch on some issues with that. But it allows more flexibility in the data science arena, but I'll talk about that more in later slides. For our data layer, everybody knows Postgres and PostGIS. I mean, I don't know anybody that hasn't used it to some extent. So that is our data warehouse for the application currently. And then at analytics layer, we're using DuckDB. And then our serving layer, I don't know if people have used Fast API yet or at all. It's great. It's a Python-based API. And then we're using some crunchy data products, PG Tile Serve and PG Feature Serve for serving up tiles to the front end. And then the front end, the consumption layer, it's I won't call it a fork of the Descartes Labs platform. It's more of a derivative, and it's using Mapbox and React. So just to talk a little bit about workflow orchestration, we did land on Metaflow, and it's really good for both observability and ease of use. To develop, it's Python with some decorators. There's more to it than that, but it really is simple to get up and running with it. It does provide a high level of abstraction, which is great for having people bring their own pipeline. It provides observability into ETL tasks and has those visualization tools. It is AI and ML friendly, which the data science group is very excited about. And then it's also scalable, so it can work with Argo workflows or Kubernetes. One issue we did run into is we use Bazel to deploy and build our images, and there's some issues with how Bazel deals with Python packages that we need to resolve. So kind of as an intermediary step, and that's mostly from an infrastructure standpoint for us. We can still use Metaflow, we can still leverage it. But instead of spinning up our own infrastructure for it, we're going to use AWS step functions. And I don't know if people are familiar with that, but that also provides its own level of observability as well. At the data layer, again, we're using Postgres and PostGIS. That's in this case, it's an AWS RDS instance of that. So some of the management of that database is taken care of for us. One big piece of the puzzle is I love the JSON-B data type. It makes it so we can store some unstructured data, and then subsequently building materialized views off of that, and doing some aggregations that way too. We also use DuckDB for aggregations, but I'll talk about that on the next slide. And then things like pgcron and pgpartman are all over the place. We would definitely want to leverage the different extensions that help us manage these pipelines. Versioning is accomplished with Alembic. So Alembic is like the Git for databases, and it uses SQL Alchemy ORMs to kind of add some structure, add some validation to, we're actually using it in our backend as well to add that data validation step. But really it's as this database matures, keeping it versioned. And then again, the PostGIS extension. The biggest reason we need this, at least currently, is because of it's a dependency of PG Tile Serve and PG Feature Serve because we need to serve those vector tiles. We're not really at present doing much leveraging those spatial functions, but we need the geometry data type, and we need to be able to use the map vector tile function as well. So the analytics layer, we're using DuckDB. And DuckDB is great. That's another thing I've heard a lot of people mention this week. It's capable of performing analysis on very large data sets, in-memory processing, and really, in the case of UNI, we're getting about 50,000 records an hour, and our alarming algorithms analyze 90 days of data. So we want to be able to do that pretty quickly. DuckDB helps us do that. The way the workflow works is we ingest the UNI data, aggregations occur, and then the alarming. This all happens in sequence, and that's then kicked back over to Postgres as a data product, the alarms. So the serving layer, we're using Fast API. It's really easy to get up and running with this. It's a Python web framework for creating APIs. What we like about it is that it's high performance and asynchronous, so we can handle multiple requests. And the other big thing that I've already mentioned is the data validation piece. And we actually use the same SQL ORM objects that we do in our Alembic migrations as our validation in Fast API. So that's a nice synergy between the two. So we can ensure anytime we make a database upgrade or add a new table or change a schema, that it's reflected in the API as well. And then PG tile serve and PG feature serve. This is how we're serving up our vector tiles, or in the case of PG feature serve is GeoJSON. But it's lightweight and performant and is basically built for PostGIS. So it's a tile server for PostGIS. And what's nice about that is you can leverage those PostGIS SD functions in PG feature serve for processing and filtering down data. Another functionality that's important for us, at least, is that we can use that database security to restrict what PG feature serve or PG tile serve can access. And there are cases where we need multiple tile servers to protect some endpoints and make sure that the right user can access the right data. And next, I'll move into a live demo. And I'm hoping for internet. Okay. So, this probably looks familiar to, let me get out of presentation modes. Okay. So this probably looks fairly familiar. It looks like a WebGIS. So this is what a user would see when they landed on this page. We have the data sets we have pulled in, at least for this front end, as the UNI data I referenced. We're also looking at Freedom House data, which is looking at how free a country is. They have their own scoring metric for different categories. So we provide links to that information. In a previous life, I worked on Landscan, so I threw that in there for some population context. It's a gridded population model of the globe. And then that open cell ID. So the user's able to kind of, change some display if they wanted to. The other piece is, so UNI provides a lot of different data sets. And these are kind of our important ones. So we want to see, who's having issue with web connectivity or what countries in Facebook Messenger and Telegram. And I'll show some examples of some interesting things there. So if I do that, Chloropleth pops up. We also just have little info for that. So if you were to click on a country, actually I know where I want to go, Bangladesh. You can just see the, change over time of, in this case, web connectivity. And if we go back to June, we can see a huge gap. And I don't know does anybody know what was going on during that time, early July of this year?
Something.
So there was protests in Bangladesh, and the government just shut the internet off. So we were able to capture that in the data, and that's really what this is trying to get at. So on the right we have our anomaly detection. We call them UNI alarms. So by clicking on one of these alarms, it will zoom you to the country, and you can get, let me change the date range a little bit. And you can see how, the change over time is happening. So in this case, our total probe count was higher than expected, and it has been for the last few days. And just to add some context, an UNI probe is somebody running the UNI application on their device, running the UNI tests to various websites and returning whether it's blocked or there's a difference in the response compared to a control. So there might not be anything going on here, but it has alarmed on just total probes. But one kind of recent news, we'll look at Telegram, and we're going to look at Signal, and we'll look at Russia, and then we'll just look at blocked probes. So this is also in the news, but Russia completely blocked the use of Signal in the country. Yesterday was a 98% blockage of people trying to access Telegram via the UNI probe app. What's interesting here is excuse me?
Please.
Signal is, it's a social media. I'm not super familiar with it.
I think privileged.
Yeah.
What is that?
Yeah. So what's interesting here, to me at least, it's kind of hard to see them. There's the alarm indicators on this time series. You can see that for about a week, maybe, or actually close to 2 weeks, it was alerting as something's going on here. But when it stopped alerting, this is the new normal. So I thought that was interesting. But the nice feature of just being able to move quickly between these alarms. Japan has had some alarms lately. Don't really know what's going on here. In fact, their total probes are up, but we're quickly digesting a lot of data. I mean, 50,000 records an hour, and these are large. These are part of the data structure we're getting back is the entire HTML response from the website they're trying to reach. So it's pretty large. I won't say big. Freedom House, this is just another example of a chloropleth, really. I'll move on to Landscan Global. And I'll put so this is a zoom dependent layer. It's not going to show you anything unless you're zoomed in with the population density. And then the other one that has a update frequency that's daily is OpenCell heat map or OpenCell ID. So these are antenna locations. And where we've used this before is, in the Gaza situation, we looked at damage assessments compared to like cell tower locations to see where there might be gaps. Obviously, that's a bad situation, so there's lots of gaps. So as we zoom in, we move away from a heat map, and we actually get the locations. And then in an actual antenna type. These are not cell tower locations, they're antennas, which a tower can have many, many antennas. And it's a pretty interesting data set. I'm right at 20 minutes, but it's essentially people are volunteering their information to say this is where a cell tower is, and it basically takes the previous record and calculates a distance from the signal and tries to refine this point on like daily. It's pretty interesting data. But that's what we're working with right now. I'll jump back into the presentation now. So lots of future work because again we've built this framework. We want to start to iterate over it. So expanding on the data sources is probably paramount for us right now. We're also looking at streaming data and implementing Kafka. On the data layer, we're dealing with multi-tenancy and is there data that certain users should not have access to, and how do we handle that? Would really like to move towards more of a data lakehouse architecture. We kind of have a pseudo data lakehouse architecture with S3, DuckDB, and Postgres, but kind of building that out, looking at using Apache Sedona and like distributing a data set across a cluster and things like that, which is also in the analytics layer there. Additional geospatial analyses, spatial modeling, asymmetric mapping, network analysis, and downsampling. At the serving layer, we're looking to do some tile caching with Varnish, and then more features for the end user. And that's it. Any questions?